Automatic, Addison.
In this tutorial, we'll explore how to create reusable motion plans for robotic arms using the MoveIt Task Constructor. We'll build an application from scratch that demonstrates how to define a series of modular movements that can be combined and reused. This approach allows for more flexible and maintainable robot motion planning, especially useful in scenarios where similar motion sequences are repeated or slightly modified. Here is what you will develop. Here's what we'll do. So our application will showcase first the creation of a reusable module containing a sequence of movements. We'll then combine multiple instances of this module into a larger task. We'll make use of both Cartesian and joint space planning. And then finally, we'll integrate with ROS2 and log the planning process. Here's a high-level overview of what our program will do. So we're going to define a reusable module that includes the following movements. First, move 5 centimeters in the positive X direction. Then we'll move 2 centimeters in the negative Y direction. Then we'll rotate minus 18 degrees around the Z axis. And then we'll move to a predefined ready position at the end. So we need to create a main test that starts from the current state and moves to the ready position. Okay, and we'll execute the reusable module 5 times in succession. And then we'll finish by moving to the home position. The reusable motion planning approach for robotic arms that you'll develop in this tutorial has several practical implications. First is manufacturing and assembly. We can create modular motion sequences for pick and place tasks or component assembly. You can use it for bin picking and sorting, where you can develop flexible routines for grabbing objects from bins with varying contents. Also, welding and surface treatment. We can build libraries of arm motions for welding or spray painting different part shapes. By mastering these techniques, you'll be able to create more flexible and efficient robotic arm systems. This modular approach allows you to more efficiently develop and adapt arm motions for various industries. If you don't already have modular CPP, you need to open a terminal, go to your ROS2 workspace, MyCobot MTC demos, go to the source folder and make sure you've got modular.cpp in there. Make sure you add the code. I've got it on my GitHub, MyCobot ROS2 package. Then once you've done that, we need to build the code. Go over here, cd ROS2 workspace and colcon build. Enter. Source the bash RC. And that's it. Okay, let's clear. Now it is time to launch everything. I've got the alias MTC_demos with my D key still getting stuck. And let's do modular. Okay, so MTC_demos and then modular. Let this puppy run. Let it come up fully. And here is what you should see. You can see the yellow going through the different solutions. Let it get to its end. Finally, move to home at the end there. Modular demo completed. Let's have a look at RViz and take a look at the results. Let's go to the top. So under reusable containers, we can see the following stages. We see current, move to ready, and then we see 5 different Cartesian path stages. These correspond to our reusable module, each containing the movement. So moving 5 centimeters in the positive X direction, Moving 2 centimeters in the negative y direction, rotating minus 18 degrees around the z-axis, and then moving to the ready position. The second column shows green check marks in the number 1 for each stage, indicating that every step of the plan was successfully computed with one solution. The time column displays the computational time for each component. We can see that the entire reusable containers took about, let's say about 0.0555 seconds to compute, with individual stages taking just milliseconds. The cost column, okay, let's click on this. Right there, you can see the cost column in this context represents a metric used by the motion planner. So for most stages, it's a very, very small value. Very, very small value. Okay. Very small value. And what does that mean? That means that these small values mean that these movements are considered efficient or low cost by the planner. This number right here consistently shows 1, indicating that each stage has just one solution. And the yellow highlighting you saw as it was running through indicates that this is the currently selected or focused stage in the RViz interface. So this breakdown allows us to verify that our reusable module is indeed being repeated 5 times as intended, and that the overall motion plan is structured correctly with initial and final movements to ready and home positions. Let's go over to the terminal window to get the detailed planning results, which you can see right here. Okay, we use the MoveIt Task Constructor uses a hierarchical planning approach. This means that it breaks down the overall task into smaller, manageable bite-sized pieces or stages and plans them each individually while considering the connections between them. You can see that here. We can see that each stage is being added to the task, including the creation of the reusable module and the 5 different instances. You can see the whole logs here from the top, each piece. Let's go down here to this block right here, analyze the output. So the root is reusable containers, and we can see that we've got 1, 1, 1 with the arrow going backwards, arrow going forwards. This means that the one solution was found and it was propagated both forwards and backwards. And for each stage, we see a pattern. We see different patterns like 0, 1, 1 and 0, 1, 0. So here, for example, the first 0 means no solutions were propagated backwards to this stage. The one in the middle, right here, indicates one solution was found for this stage. And the last number, which is either a 0 or 1, shows whether this solution was propagated forward to the next stage. The Cartesian path stages right here represent our reusable module, and each show a 1, 1, and a 1, meaning they received a solution from the previous stage, found their own solution, and then passed it to the next stage. Then within that, we've got the individual movement stages, x plus 0.05, y minus 0.02, and rz minus 18 degrees. Within each Cartesian path, we see that, and we see a 0, 1, 0, indicating that they found a solution but didn't need to propagate it either forwards or backwards. Then we've got the move to ready stages at the end of each Cartesian path, which show 0, 1, 1, meaning they found a solution and passed it forward to the next or final stage. So these results demonstrate that our planner effectively generated solutions for each stage of the task, including 5 repetitions of our reusable module. The hierarchical structure allowed the planner to solve each part of the problem independently while maintaining the overall sequence of movements. Pretty cool. And then we've got the stage summary right here at the end. The stage summary indeed confirms that each major stage, okay, the current, move to ready, the 5 Cartesian paths and all that, move to home, found one solution and 0 failures. So this indicates a successful planning process for our entire reusable motion sequence. So by examining these results, going really deep into the logs, we can see how the modular approach allows for efficient planning of complex repetitive tasks. Each instance of the reusable module is planned independently, but within the context of the overall task. And this ensures a cohesive and executable motion plan for the robotic arm. Now for the detailed code walkthrough, let's go ahead and have a look. Modular.cpp. Here we start off with our comprehensive comment block outlining the file's purpose. We demonstrate the use of the MoveIt Task Constructor for robot motion planning. We introduce a key concept, the serial container right here, which is used to create reusable modules of movement stages. And the file includes the necessary headers for our ROS2 and MoveIt and the Task Constructor library we can see here, lines 19 through 28. This establishes the foundation for our modular motion planning demo. We've got the create module function right here, which creates a reusable module for a robot movement. Sets up a serial container, line 41, named Cartesian path, and we configure it with 4 stages, which I've labeled on lines 50, 62, 674, and 86. We've already discussed those stages, and each stage is created using either stages move relative, like that, or move to. Move to, like on line 88. So we configure it with the appropriate movement parameters and then add it to the container. Next, we have the create task function. This creates the main task for robot movement, sets up the task structure. So we add the current state as the starting point. We move to the ready position where the arm is kind of like at a 90-degree angle, ready to grasp. And we've got 5 instances here, 5 instances of the reusable module created by create module. And then finally, we move to the home position, which is that erect standing up position at the end. So this structure creates a sequence of movements that the robot will perform, repeating the same set of actions 5 times in a row. Got the main function, okay, where we initialize ROS, create a separate thread to handle ROS2 callbacks. Line 166, allowing the node to process incoming messages and services. So this is the meat right here. We have the create task. Okay, task is created right here. Code then attempts to plan the task, line 173. Got a lot of good results handling and logging, comprehensive logging of the planning results, including the number of solutions found, the task state, and the summary of each stage performance. We've got a lot of error handling to catch and report any exceptions that occurred during the planning process, including detailed task information in case of failure. And then completion down here. The program waits for ROS2's spinning thread to finish before exiting. That's it for this tutorial. Thank you for watching and keep building.